sine curve. Did you guys see a sine curve at all last year? No. Cool. Excellent. Alright, what I've drawn or given you, and I'm sorry the printing hasn't come out very well, is a graph. Regular graph. Here is x and here is y, or you can think of it as f of x. And what we're going to graph is the line y equals sine x. And you might notice something strange about the axes. Instead of labeling the axes 1, 2, 3, 4, etc., I've labeled them in fractions of pi. So pi on 2, pi, 3 pi on 2, 2 pi. And you might notice that if we really wanted to, we could put in intermediate markings of like pi on 4 or 3 pi on 4 and go up in quarter pies if we really felt like it. Alright. This is a unit circle. And we're going to start off our story with x equals 0. X equals 0 is there, and I'm going to do a little table. You know how in graphing linears or graphing quadratics you quite often did a table, and the table looked like this. X, y. When x is 0, and we're looking at the equation y is sine x, if I put 0 in there, how high are we? What is the y value?
1.
0, we're 0 high. Here we're 0 high. Alright? Then, what about pi on 6? What is sine of pi on 6? How high are we at pi on 6? And pi on 6 is about there. Yes. It's my favourite one. It's one we've seen before. We're a half high. What about pi on 2? There's a unit circle on the page, but you want sine of pi on 2?
1.
Good. 1 because we're at the top. Now, I'll try and graph them on this graph. That's a half, that's 1. When x is 0, y is 0. When x is pi on 6, y is a half. When x is pi on 2, y is 1. Don't connect them yet, but put some dots. Then, what about 5 pi on 6? So we're around here now. Sine of 5 pi on 6 is a half. What about sine of pi?
0.
0. Cool. So, 5 pi on 6, sine of pi is 0. As we continue around, I'll go to the negatives now. Here is 7 pi on 6. At 7 pi on 6, we're all of a sudden down to minus a half. 7 pi on 6 lands us there. Here, at 3 pi on 2, we're at minus 1. The graph is rather trippy. It does this. At 3 pi on 2, it's at a minimum of minus 1. At pi on 2, it's a maximum of 1. At pi and 2 pi, it's at 0. And if you felt really like graphing it, at 2 pi we start going around the circle again. This pattern repeats. And you've just hopefully drawn your first sine curve. If mine by hand drawing looks dodgy, what you're aiming at is this. Through 0, pi on 2, pi, 3 pi on 2, 2 pi, and it keeps going. sine x makes this curve that goes forever, which is pretty cool. Now, there's some notation around this, and a lot of the notation that we use here is similarly used for physics and science. So, have you guys come across amplitude in science?
Yeah.
The amplitude of a wave? Maybe? Amplitude of a wave is how high the wave is from the centre line. So that is the amplitude. On your diagram, probably fits neater on mine, that is amplitude. Another one here, or phrase we use, is period. Period refers to how often this repeats, how periodic it is. A period is the time for one full revolution. In our case here, the period is equal to 2 pi. Yes?
Is that the same as frequency?
Yes. I think so. Yes?
How do you know that it reached like 2 pi?
You got back to here?
Yeah.
I guess because if we follow this point around, pi on 2, 7 pi on 6 here, sine of 2 pi means we're back at this point. So we're 0 high. So we've come up from the negatives, or come up from the negatives to get back to there. And then the rotation starts again. Alright. Before I go further, I want to jog your memory. Remember transformations. What you learnt with transformations of other functions also works with trig functions. So, if we look at this graph here, any guesses what's going to happen if I add 1 to the end? Just do a little plus 1. Yeah?
The whole thing will be done.
Beautiful. Plus 1, the whole thing moves up 1. So a plus d on the end translates the entire thing up 1. Similarly, I could do a minus 2 on the end and drop the whole thing down 2. So everything that works on the sheet still works. What about if I did plus pi on 2? And I will compare that to the old one. The OG is the green one. If that's the original, adding pi on 2 has the impact of moving it left pi on 2, which because it's repetitious or periodic, it actually looks exactly the same as moving it right pi on 2. So I maybe chose the wrong thing there. But if I chose, how about this one, we just add 1 on. That is moving 1 this way. It's not as obvious because it's on fractions of pi, but a plus 1 shifts the whole thing left and right. So, without doing a lot of drawing, adding on the end, adding and subtracting in the brackets moves the thing up and down, left and right. So we're starting to move this curve around. Then comes a more interesting thing, negative. What if I put a negative in front of it? Any guesses what will happen? Good, it flips. So, green's the original, and negative in front flips it. It's a reflection in the x-axis. I struggle to visualize the next. What happens if I put a negative in front of the x there?
That's the same.
Yeah, it's just... Actually, it's not like that at all, is it? It is. Oh, it's not the same. It's a reflection in the y-axis. So, it went from being green, the original, pi on 2, 1, to reflecting there, and reflecting here. So, it basically looks like the same as the other x. What other transformations do we have? Alright, last two transformations perhaps the most important. An a at the front. What happens if I put a 2 at the front here?
Vertical dilation.
Good. Vertical dilation, stretch. If I put a 2 at the front here, the maximum is no longer 1, it's now 2. So we would say this number at the front controls the amplitude. It went from being 1 high, because there's a 1 at the front, to being 2 high. Or being 3 high. Yeah. What about putting a number in here next to the x? What did that happen? What would that affect on our other functions? Yeah, horizontal stretch. So if I put a 2 there, it shrinks it, halves it. So where it was a repeat of 2 pi, you see how the green repeats once within 2 pi? The blue is being concertinaed, it's repeating twice within 2 pi. If I put a half pi in there, rather than it repeating once within 2 pi, it only repeats half within 2 pi. So this here impacts the period. And our textbook kindly summarizes all of these changes on the next page. But the important thing is recognizing that what you learned is just applied to a trig function to do this. The A in front affects the amplitude. How much up and down? The B here in front of the X affects the period. How long it takes to repeat. The C affects horizontal translation. The D, how far up and down it goes. Those are basically from the first topic of function transformations, just applied to a trig graph. Few other notations. The principal axis is the one that it rotates around, and it will rotate around D at the end here. You saw when I did a +2 on the end, the whole thing moved up 2, that's the principal axis. The period is 2 pi on B, and the amplitude is the size of A. Those straight bars are the modulus, meaning how big A is. So if A was -3, the modulus, or those bars of -3, is 3. It's asking for the size of the number. And we're going to use this quite a bit. Before we use this, I would like to briefly introduce cosine graph. So, turn over. Let's repeat the same thing with cosine. And I will actually do it on the screen. Starting at, oh, let's make a nice big and red. What is cosine of 0?
1.
1, nice. Cosine of 0 is 1, so I'm going to put it there, this being 1 high. Cosine of 0 is 1. What is cosine of pi on 2? 0. Lovely. Cosine of pi? Good. -1. Cosine of pi on 2? Just here. 0. Cosine of 2 pi? 1. What you might notice, even with my terrible drawing, I'll flip it to Desmos, is that sine x and cos x are the same graph, they're just translated by pi on 2. There's a shift of pi on 2. The purple one's cos x. It starts at 1 because out here at x equals 0, cos is 1, and then it reduces. Sine starts at 0 and increases. Everything we just talked about the sine function is true about the cos function. The A at the front, the B and the C and the D moving in those particular ways is true for cos. Sine and cos are very, very, very closely related to the point where you model things in real life, everyone just uses the sine curve. For some reason sine is the default and poor old cos gets left a bit behind. But if you can do it with the sine curve, then cos doing it with the cos curve is basically the same. Where things get a little trippy, and we're not going to spend a lot of time this year or any year, is with the tangent. The tan curve is this, sine x divided by cos x. So you're taking the green line and dividing it by the purple line. So 0 divided by 1 is 0. There's fine. Here they're the same, which is where it's 45 or pi on 4, so tan will be 1. Here it's yucky, because you're doing 1 divided by 0 is undefined. Tan is incredibly unpredictable and not that useful for modelling stuff. Like this here, these patterns will indicate the amount of daylight we get in a day. Towards Christmas it's a maximum, right now it's a minimum, and spring and autumn it's about in the middle. Same if you've ever seen a tide chart. This maps tide, it will map your hormonal levels, it will map lots of things that have a rhythm to do with the day or rhythmic and periodic. Tan is less useful.
It's on the tangent.
Yes, it's asymptoting at pi on 2 and 3 pi on 2. Each of these are asymptotes.
It aligns with the tangent.
Yeah. And so we're not going to use tangents a huge amount. It's worth being aware of it. It's worth knowing that, for instance, it repeats every 1 pi rather than every 2 pi. It goes off like crazy. I've given you a space on your graph paper to optimistically try and draw it. Have fun with that. I will zoom in a little bit. Have a crack. But I'm well aware that no one's going to draw a very good tan curve. That is just fine.
A bit like that.
Why is it only tangent to sine and not cos?
Interesting. I guess because at that particular point, it's 0 divided by 1, which is 0. It's the only time when they equal. And that will be here as well, 0 divided by 1. It's where tan equals sine. There is a neat shortcut here. You see how it approximates the sine curve for very small values of x? If you meet a scientist, they will say tan x is about the same as sine x for small values of x. It's a shortcut they use with astronomy sometimes, just because dealing with sine is better than tan. If you're looking at very small angles around stars, it's basically the same line. So they do use it as a neat approximation.
But in astronomy, if you're like off by a bit, you'd be off by a lot.
Yeah, it's not the greatest approximation, but for tiny, tiny values, it holds about true.
What's considered tiny?
Oh, like millionths of a radian. Like, tiny. Alright. Oh, I think I've lost my work. Turn over. We're going to look at the investigation. I really hope I saved it. How incredibly annoying. Alright. For your investigation, what you're going to do is you're going to get an image of the Harbour Bridge. Here's one I used yesterday. And I'm going to get another image. And what you might notice is that if you turn your image over pi radians and do a bit of manoeuvring, can you vaguely visualize that looking tiny bit familiar? Sadly, yeah. It turns out, you know how when you were trying to fit your quadratic to the Harbour Bridge and it just wasn't fitting? It's because the Harbour Bridge isn't a quadratic in shape, it was never going to fit. We stitched you up in part A. We asked you to do something that wasn't doable. Instead, the Harbour Bridge much more closely approximates half a sine curve. i.e. that half, I just put another one on here to make it more obvious. Now, I want to try and make it a bit like your image. So your image has, them not 7 high, doesn't it? So for some reason in your image I put them up here, about there, and about there. And they go out 19 long, 5 pi is about 15, but we're just going to do this. Alright. Your starting point for part B is what's known as the general form of a sine curve. The general form of a sine curve is y is a sine b x takes c plus d. It's that thing we saw on the previous page. And I would do it in the following order. I would find d first. D is principal axes. So, you're going to start off with y is sine x. And then I want to centre my curve about where the middle of the bridge would be. So I'm going to do this fairly rough, but you guys can do it more carefully. In this case, plus 7. It's not perfect, but that's a good start. 7. Then I want to fix my amplitude. My amplitude is the gap between the centre line and the top of the bridge. Currently it's 1, because A starts off at 1. Really I want it to be 1.6-ish. So A, his amplitude is 1.6-ish. We've done by eyeball, but we'll see how we go. 1.6. Oh man. Alright. 1.6 is a bit high, isn't it? Because I only want it to be there. 1.4.
It's a bit lower on the other one.
It is a bit lower on the other one. So maybe my 7 wasn't quite right. Maybe I owe 6.8. That's better. There's going to be some trial and error. The important thing is you're not just putting in numbers blindly, you're having an understanding of what each number does as it goes in. I quite like to move this across to there. So right now it's what? Half pi. I want to move it across to a full pi across there. So I want to move it across a half pi. So how do I move it right, half pi? Good. I'm going to put bracket minus pi on 2. To get pi on canvas, oh sorry, Desmos, you just type in half pi. Alright, half pi was not quite right. I want half 1.1 pi. I want 1.3 pi. Sure. I'm trying to land that on there, which I haven't entirely succeeded in doing, but I'm getting close. I might change that to 1.7. Then, I want to stretch this out. And this is where the first sort of actual algebra piece of maths comes in. Your period is equal to 2 pi over b. The period is why we've done 2 bridges here. My period here is about 5 pi. So if I want this curve to repeat once fully in 5 pi, I set my period to 5 pi. It doesn't have to be a fraction of pi. You might look at your bridge and think it repeats once in 30 units. You set your period to 30. This equals 2 pi on b. If I multiply by b and divide by 5 pi, b is 2 pi on 5 pi is 2 on 5. If I put b in there as 2/5, it should stretch out so that it repeats once over that 5 pi. So let me try that. That's not what I meant. Alright, it's getting there. but my moving clearly failed. I want it to go back there. So I'm going to take that back off. Oh, it's close. I'll move it. So, it's not perfect, but you're not going to watch me nudge digits around. The important thing is you manipulate each of these four until you get a shape that follows it closely. And then for part B, same as part A, you're picking the x values of the left-hand or right-hand cable, whichever one, substituting it in. Again, your Excel can help you with the substitutions. You can just copy the entire table you used for part A, use it for part B, but change the formula. And then sum these up, and you'll get a value for each of those lengths. And that is all part B. Part B is basically repeat part A, but this time use trigonometry, or use a sine curve. Part C is where a little more creativity and a bit more difference comes in, but aim for part A and B first. A with quadratics, B with trig. That makes some sense? In terms of the actual questions for today, there are not many, and there's only a very small amount of chapter to go. We're going to skip bits of the chapter, so I'll send out a Canvas announcement of what we're actually fully covering in the topic. It's the term plan on Canvas, but I'll send out a different one. How short of them? For today it's these, and then your investigation. Is that good? Questions?